Okay, today's experiment is the last experiment in our cycle, that is experiment number 10, that is class C tuned amplifier. There is a little theory, let me read it. In class C operation, collector current flows for less than 1/2 cycle of the input signal. The class C operation is achieved by reverse biasing the emitter base junction, which sets the DC operating point below cutoff and only allows the portion of the input signal that overcomes the reverse bias to cause collector current to flow. In the theory class, it is already discussed and you will have to recall it now that class A works for 360-degree cycle, class B is 180-degree cycle, class AB is in between 180 and 360, whereas class C is less than 180-degree. That means the amplifying transistor will not conduct even for half cycle, it will be less than half cycle, by means of which we are saving a lot of DC power, and that is how we have highest efficiency here. Out of class A, B, AB and C, class C is having the highest efficiency, nearly 90% efficiency. When I discuss the circuit diagram later on, I will elaborate about this particular point. The class C operated amplifier is used as a radio frequency amplifier in transmitters. The reason is, when the amplifying transistor is conducting for less than half cycle, then the input signal will not be faithfully amplified by the transistor, because only for part of the input signal the transistor is conducting. For the remaining portion of the input signal, the transistor is not conducting at all. So the shape of the waveform will not be as same as the input waveform. That is called as amplitude distortion. Now, this amplitude distortion is all right in the case of radio frequencies. That is what is mentioned here. It can be used as a radio frequency amplifier in RF transmitters, even in RF receivers also. So the point here is, in the RF domain, the shape of the carrier is not important. For example, when you travel in a vehicle, the vehicle is carrying you all the way. Vehicle is a high speed equipment, so to say, and you are a low speed mover, so to say. So you are sitting either on top of a two-wheeler or inside a four-wheeler or inside a six-wheeler also, or inside a metro train also, inside an aeroplane also. Now that vehicle is carrying you. Now that is the carrier. You are the one who are traveling inside the vehicle. So you are like a modulating signal now. So in the case of RF applications such as AM radio or FM radio, or even in case of 3G cell phones communication, the voice signal is important. Voice signal is the one which is being transmitted. For example, right now I am speaking, my voice signal is being transmitted through the wired medium or through the Wi-Fi medium all the way till your ears. So my voice signal is right now undergoing modulation, and there a high frequency carrier is being utilized in between you and me for communication. In the similar way, when you travel in a vehicle, your shape or your size or your health is more important or most important. The shape of the vehicle is not that important. For example, when you travel in a BMTC bus, the BMTC bus's shape is not actually so important for you. At times it may be important based on the class of traveling which you want to have. Some people go in Volvo buses, some people go in regular BMTC buses. That is up to us as commuters. But main thing is the safety of the vehicle. The shape of the vehicle is not that important as the safety of the vehicle. In a similar way, if I have to have that analogy here again, the shape of the carrier wave is not important here. Carrier wave has to carry the information signal from the source to the destination. But the shape of the information signal is important. So for amplifying the information signal, we have class A amplifier only always. That is called as pre-amplifier. But later on, after modulation, when we have to amplify the modulated signal, which has to be traveling through the communication channel, maybe a wireless channel or a wired channel. There, the shape of the radio wave is not that important because the shape of the radio wave is anyhow going to change during modulation. Maybe AM or maybe FM, or even in digital modulation such as ASK, FSK, PSK or QAM. These are the advanced modulation methods. You are going to learn more about them when you come to third year engineering in electronics and communication. So the point to be stressed here is the shape of the carrier wave or the radio wave is not that important when compared to the shape of the information signal. So for amplifying the information signal, we will use class A amplifier, where we can have maximum 25% efficiency, or if it is transformer coupled, we can have up to maximum 50% efficiency. But the power in case of radio transmitters is going to be expensive or costly. In an audio amplifier, we can have a 10-watt amplifier, 20-watt amplifier. But in the case of a radio amplifier, a 10-watt radio amplifier is much more expensive because it is working in high frequencies. For high frequency devices, the cost is larger. So in such case, if we have to reduce the cost and increase the efficiency, let us say, we can reduce the cost. Instead of going for a 10-watt RF wave, 10-watt RF wave is going to be much more expensive. Let us say we want to reduce the cost. We have to increase the efficiency of the amplifier. Now we increase the efficiency of the amplifier by compromising in the shape of the carrier signal. That is why the class C operated amplifier is used as a radio frequency amplifier in transmitters. The two primary items that determine the class of an operation of an amplifier, the amount of bias and the amplitude of the input signal. With a given input signal and bias level, you can change the operation of an amplifier from class A to class B just by removing the forward bias. Also, a class A amplifier can be changed to class AB by increasing the input signal's amplitude. So, in the theory classes also I have been telling you, class A amplifier will be generally used for audio applications where efficiency is less but signal quality is much better. And it conducts for complete 360 degree. We increase this input signal amplitude. That means a pre-amplifier is gradually becoming a power amplifier in case of class B or class AB or class C, where the input signal amplitude is increased. If input signal amplitude is increased to the point that the transistor goes into saturation and cutoff, it is then called an overdriven amplifier. You should be familiar with two terms used in conjunction with amplifiers. One is fidelity and efficiency. Fidelity is the faithful reproduction of a signal. I have been telling you about faithful and unfaithful amplification. In case of class B, class AB and class C, it is unfaithful amplification. Fidelity is the faithful reproduction of a signal. In other words, if the output of an amplifier is just like the input except in amplitude, the amplifier has high degree of fidelity. The opposite of fidelity is a term we mentioned earlier as distortion. Therefore, a circuit that has high fidelity has low distortion. In conclusion, a class A amplifier has a high degree of fidelity. In class AB amplifier has less fidelity, and class B and class C amplifiers have low or poor fidelity. That is when I mentioned the shape of the carrier wave is not that important when we give more importance to efficiency. The efficiency of an amplifier refers to the ratio of the output signal power compared to the total input power. The input power is complete DC power, output signal power is AC power. An amplifier has two input power sources, one from the signal and one from the power supply. Since every device takes power to operate, an amplifier that operates for 360 degrees of the input signal uses more power than if it operated for 180 degrees of the input signal. By using more power, the amplifier has less power available for the output signal, thus the efficiency of the amplifier is low. So in class C tuned amplifier, we increase the efficiency by going for a distortion in the output signal. You are seeing the circuit diagram now. Let me explain the circuit diagram. Now when an input signal is applied, let me annotate. When an input signal is applied like this, you can see that there is a pull down resistor R1 and there is a input DC blocking and AC passing capacitor C1. So now, if this is our input AC signal, because of this R1 now, there is a loss of signal to the ground. So let us say until this base point reaches 0.7, the transistor will not turn on at all. So let me change the color to show you. Let us say we are applying an input signal. Let us say up to this point, the transistor will not turn on at all. That means the transistor is conducting from this point till this point. You can see here, out of the total 360-degree cycle, the transistor is conducting for less than 180 degree. That is why it is now class C. That means when the signal crosses above 0.7, that too, it should be crossing above 0.7 at the base. That is because of this R1. If the value of R1 is lesser, the conduction angle can be still lesser. Conduction angle is the angle up to which the transistor is conducting. You can see it is less than 180 degree. It can be made still lesser by reducing the value of R1. Now, because of this, the SL100 transistor, amplifying transistor, conducts for a small duration of the input signal. Now, when this SL100 conducts for that small duration, you can see you have these two energy storage elements, one capacitor and one inductor. Now, as soon as this SL100 conducts, you know that inductor passes DC. So, from VCC, DC was flowing, but DC is flowing because of the conduction of the SL100 now. Now, after that, in the other portion of the input signal, SL100 turns off. But when that SL100 was conducting, because of the energy storage in the inductance, now when the SL100 turns off, the same energy stored in the inductance and the capacitance gets released to the output. Which means inductance stores electromagnetic energy, whereas capacitance stores electrostatic energy. Now we are using them together. This capacitance will not pass DC normally when there is a VCC connected. But what happens when transistor turns off? When transistor turns off, the energy stored inside the inductor is also going to be coupled to the capacitor as well, right? Now we have a parallel resonant circuit here. L and C are in parallel. It's a parallel resonant circuit. That is why now this is a tuned amplifier. It is called as class C amplifier because the conduction angle is less than 180 degree. Why is it called as tuned amplifier? Because we have a formula now. F equals 1 over 2 into pi into root into LC. F equals 1 over 2 pi root LC. That is because of this resonant circuit, which is a tuning circuit. Which means now we have made class C amplifier as a tuned amplifier also. In general, class C amplifiers are normally tuned amplifiers only. The reason is we are using them for specific applications. For example, right now when my speech is reaching you all the way, let us say we take the example of Wi-Fi itself. Let us say through Wi-Fi, if the speech is moving, now the carrier frequency used for Wi-Fi is 2.4 gigahertz. So carrier frequency is 2.4 gigahertz only. So this L and C can be chosen in such a way that the F is equal to 2.4 gigahertz. Which means class C amplifier is normally a tuned amplifier, means it is a narrowband amplifier, as it is used for a specific application only. If you want it to tune to other frequencies, you can have a tunable capacitor here. In the olden days, the radio receiver used to be having a tuning control where manually people used to tune to different stations by means of a capacitor called gang capacitor. Now anyhow, in your mobile phone, you have DSP. Because of the digital signal processing, now all the tuning that happens is just by means of the DSP, digital signal processor, where digitally tuning is happening, and now the things are really very easy. There is no gang capacitor nowadays inside any radio equipment as such because of the digital revolution. So class A amplifier is basically a tuned amplifier. It can be designed for a particular application. Now, when this transistor is conducting for less than 180 degree, so let us say only for this much portion, when the transistor is conducting at the output, let me write the output waveform. Now at the output, corresponding to that output input wave, corresponding to this input portion, you will have an output wave. Remaining portion, you will not get it as such. Why? If at all I have to write the waveform like this. At the output, only this much portion is there. Let me change the color again. At the output, you will see there is a drilling activity happening here. Just a minute. Now there is a drilling operation happening here. I cannot help it as such. Okay. There was a drilling operation happening here, and as there's a disturbance, I cannot help it now. Now we have asked them to do it after about half an hour. Anyway, until then, let us peacefully continue. Within the next half an hour, anyhow, I am going to end this lab. To continue now, when the input signal is less than 180 degree, only then the output is available because the transistor is conducting at that time. As you already know, this is a common emitter amplifier which is going to give 180 degree phase shift. So that is how you can see this output signal there. But what about the dotted line? The remaining portion of the output is not available as such because the transistor is off. But during this condition when the transistor was on, energy was stored in the inductance, and what happens later on is the energy stored in the inductance is going to be released to the output. You can see that load resistance there. When it is released to the output, and this output circuit is a tuned circuit as such. It will have a minimum resonance only for the tuning frequency. Now in this case, it is a parallel resonant circuit. So it is a tuned circuit, so it will have a highest gain only at the tuning frequency. That is how now it is a class C tuned amplifier. But because these LC elements are going to release the energy that is stored, the shape of the output waveform will not be purely a sine wave. Input was a sine wave. Output will not be a undistorted sine wave. There will be a distortion in the output. But as I have mentioned you earlier, the distortion can be compromised in the case of radio frequencies as we get higher efficiency. You can see as the DC current is flowing, only it was smaller time duration. It is not working for a complete 360-degree cycle. That means only when the transistor is turning on, DC current is being drawn. At all other times, transistor is off, and that is how the power is going to be saved. That is the efficiency is nearly 90%. That is the reason one milliampere is connected here, one ammeter is connected here to measure the RMS current, I should say, or DC current that is flowing through the transistor. We can measure the DC current through the ammeter itself because we are working with radio frequencies. So when we work with radio frequencies, it does not matter about the average current here. Anyhow, the ammeter is going to show the average current only because the transistor is working in a very high frequency. That's the idea here. So do you have any questions here? If you have any questions, you can ask me. Otherwise, I will proceed. Okay, as usual, there will be no questions. So let me proceed. Let me discuss the design. Let us say the frequency is 150 kilohertz. 150 kilohertz means it is radio frequency. It can be more than that also. Now corresponding to 150 kilohertz, T is 6.66 microseconds. So this R1, C1 at the input, the time constant at the input must be larger than this T. So let R1, C1 be 100 T. Now choose C1 as 0.01 microfarad, then R1 can be 66.6 kilo ohms. We can choose the standard value of R1 as 68 kilo ohms. As I told you, the value of R1 actually matters when we try to control the conduction angle of the transistor or the amplifier. So in general, tau must be much greater than T. Tau or time constant is R1 C1, that must be much greater than the time period of the input signal. That is how we choose C1 and R1. Now for the tank circuit, why do we call it as tank circuit? Because tank generally means storage of water. Water tank means storage of water. Same way tank means storage for anything else. Here this LC itself is the tank circuit, it is storing energy, electromagnetic as well as electrostatic energy. So that is going to be released when the transistor is off. So if F is equal to 1 over 2 pi root LC, now substituting that 1 over 2 pi root LC is not actually visible here. I think when they prepared this lab manual, they've copied the formula or image from elsewhere, which is not done properly here. Anyway, let me write it. It has to be 1 over, let me write it clearly using a pencil. It has to be 1 over 2 pi root L C. So if it is F equals 1 over 2 pi root L C, it is 150 kilohertz. Let this C be chosen as 0.001 microfarad. Which is this C? The C at the collector is 0.001 microfarad. Then L, we will obtain it as 1.125 millihenry, nearest to 1 millihenry. Then F actually is going to change to 159 kilohertz because of a slight change in the values. So R1 is 68 kilo ohms, C1 is 0.01 microfarad, C is 0.001 microfarad, and L is equal to 1 millihenry. That is the design of our circuitry here now. Now checkpoints. Check the transistor, adjust input frequency exactly equal to tune frequency, observe the clamp signal at the base of the transistor. Actually, you can connect the oscilloscope across this R1 and you can actually find out up to how much input signal the transistor is turning on. The same can be observed even at the collector by connecting the oscilloscope here. So procedure is connections are made as shown in the diagram. Adjust the input frequency for the applied DC voltage, adjust the amplitude of sine wave signal so that the output signal peak to peak amplitude twice the DC voltage. We will get twice the DC voltage here. Compared to VCC, we will get the output as 2 VCC. That is because whenever SL100 is off, the VCC is available by means of the inductance. How it can swing from 0 to VCC? That is because the energy storage elements are going to release the energy later on, and when the collector is at VCC normally, when the transistor is off, on top of which the energy stored is going to be superimposed. So naturally it is going to be 2 into VCC. So we will have a peak to peak swing at the output of 0 to 2 VCC. Now where is the load resistance? Around 10 kilo ohms. It is not 10 kilowatt, it is 10 kilo ohms. This load resistance can be varied from 0 till 10 kilo ohms or even more than that to find out the optimum load. I had mentioned earlier also that when the load impedance matches with the source impedance, then only maximum power transfer happens. So we can find out the optimum load for the circuitry by varying the load resistance. Now note V out, VDC, IC and RL to find PAC and PDC, finally the efficiency. PDC, PAC divided by PDC is going to be the efficiency. Output voltage you will know, output current you will know, and load resistance you will know, voltage DC you will know, that is VCC itself. So using that we can find out PAC by PDC, that is going to be the efficiency. Now the ideal graph is something like this. That means at a particular value of RL you will have a maximum efficiency, beyond which efficiency will reduce, below which also efficiency will reduce. So we can have the observation table like this. For a given value of load resistance, output voltage can be measured using oscilloscope, or even during simulation also. Even in the simulation through PSpice you can measure it. Collector current is measured, VDC is VCC, so AC output power is V0 square divided by 8RL, where V0 is the peak to peak output voltage. PDC is nothing but VCC into IC. VDC is nothing but VCC. VCC into IC. So efficiency is PAC divided by PDC. Now that is the final output. Okay. Even though I showed you experiment 11 that we had already discussed earlier, amplifier using JFET that we had discussed earlier. So no need to discuss it again here. So this is the end of today's class where we discussed class C tuned amplifier. And this can be hardwired or simulated also. If you want, you can connect it as a hardwired experiment and you can actually see all the waveforms using oscilloscope, which is a simple experiment actually. Connection wise, there is not much of a difficulty for you. Or if you want, you can use PSpice also, you can simulate this experiment. It is up to you. So we will see about it when the offline lab classes start. We can do both now. In the same lab class, initially we can have a hardware experiment, later on we can have a simulation experiment for the same circuit. So if you don't have any questions, I am going to end today's class. Any questions here? Okay. Yeah, tell me.
Get the value of R1 for a pair.
Okay, R1. See, this at the input side we have this R and C. Generally, any RC circuit will have a time constant tau. For example, let me annotate. Here, this tau is generally time constant tau is R into C. Wherever any C is there, any R is there, whenever input signal is there, the capacitance will charge through R and then the capacitance will discharge through the same R. That is called RC time constant, or in general we call it as time constant tau. Now this tau must always be much greater than the input signal for the normal operation of the amplifier. Tau must be always greater than T, where T is what? T is the period of this waveform. We have this input wave. Its period is now T. So always this RC must be greater than T. Why? Let us say RC is less than T, then this RC itself is going to block all the input signal. No signal will reach to the amplifying transistor also. That is the idea here. If the time constant of the RC circuit is equal to the time period of the input signal, the time constant circuit itself or the RC circuit itself will absorb all the energy of the input signal. So the frequency of the input signal must be much larger in such a way that it will overcome the RC time constant. Now frequency is inversely proportional to time period, right? So that way tau must be much greater than T. only then the input signal will properly reach the base of the transistor. That is the idea here. That is how we have this tau is equal to RC must be much greater than T. RC is nothing but tau. Tau must be much greater than T. Let us assume that RC must be equal to 100 T for our sake. When we take it as 100 T, let us assume the value of C1 to be 0.01 microfarad for our sake. 0.01 microfarad is nothing but 10 nanofarad. 10 nanofarad ceramic capacitor is normally available with us. So we connect a 10 nanofarad here. For a 10 nanofarad capacitance, we can get the value of R using this formula. You can change this also. If you, instead of 10 nanofarad, let us say you choose it as 100 nanofarad. Now R will become different. Let us say if it is 0.01 microfarad, then it is 68 kilo ohms. If it is now 0.1 microfarad, now this will be 6.8 kilo ohms. That is the difference there. So that way we decide R1 and C1. I hope I answered your question now.
Yes, sir.
Okay. Any other questions? Okay. As there are no other questions, let me stop recording now. And Prithviraj sir has already put an attendance link there. You can answer your attendance there. We will go into mute mode. You write your observation book and you upload the PDF into the Google class. I will be stopping the recording now, but the meeting will be on.